Okay, so like we have for a lot of issues of convergence, we're going to demonstrate a connection between a Cauchy criterion and convergence. And this has the same sort of usefulness as it does with sequences of real numbers or series, where you may want to show that something converges without access to what it converges to. And that's when a Cauchy criterion is useful, because the Cauchy criterion just involves showing that the terms get closer together, not necessarily having to know what they converge to. So in the case of uniform convergence of sequences, we say that a function sequence converges uniformly to f1a if and only if, so this has to go both directions, for every epsilon bigger than 0, there's some capital N, so that if we go out far enough in the function sequence with m and n, the difference between fn and fm is smaller than epsilon. And again, this is a crucial part, for all x in the set at the same time. So if fn converges uniformly to f, the Cauchy criterion holds, and if the Cauchy criterion holds, fn must converge uniformly to f. So this is going to provide us a way of showing uniform convergence, even if we don't necessarily know what the function sequence converges to. So let's start off with the forward direction. We assume f sub n converges uniformly to f1a, and we show that the Cauchy criteria has to hold. So let's let epsilon be bigger than 0 and consider the thing we want to make small. So this is fn of x minus fm of x. And let's do kind of our standard trick. We're going to add and subtract f of x. Inside the absolute value. And so if we come crashing through with the triangle inequality, then I get two pieces. And then we use the fact that fn is converging uniformly to f, so there's some capital N such that if we go out far enough in the function sequence, we can make each of these pieces less than epsilon over 2. So take n sub epsilon by definition of uniformly convergent. So that this is less than epsilon over 2 plus epsilon over 2, which equals epsilon, and that establishes the Cauchy criterion. All right, so being a little crowded here, I've left out some of the words that we would normally include. We would take capital N sub epsilon by the definition, so that if little n is bigger than or equal to capital N, we can make the difference less than epsilon over 2, and then we do that for both pieces at the same time, and that should do it. All right, next up is a little bit trickier. So we want to prove the backward direction. We assume that the Cauchy criterion holds, and we want to show that the function must converge uniformly. Now, the first thing here is by the regular Cauchy criterion for sequences, we do know that there has to be a pointwise limit to my function sequence. So there has to be some f to which the fn's converge at each point x. We just don't know yet whether that's uniform convergence. Right? We do know that we have convergence pointwise at least. All right. So by definition of the Cauchy criterion, there exists some capital N sub epsilon such that if m and n both bigger than capital N, we can make Fn minus Fm less than epsilon over 2. Right, so we have let epsilon be bigger than 0. Squeeze that in up here. Standard part of the proof, but it's good to have it written. So if we let epsilon be bigger than 0, we start off using the definition of Cauchy criterion for uniform convergence. And we know we can make the function difference less than epsilon over 2. We'll see the reason for the over 2 in a minute. Right, so if this is true for all m and n bigger than capital N, then it's true for the limit as m goes to infinity. And in the limit, right, we know that each individual term is less than epsilon over 2, but in the limit it might actually equal epsilon over 2. So finishing this up, if we take the limit as m goes to infinity of f sub m, then by what we said before, we know there's a pointwise limit and it equals f. And that difference is less than or equal to epsilon over 2 for all x at the same time. And epsilon over 2 is strictly less than epsilon. This is for n bigger than capital N and x in A. So that is the definition of uniform convergence, because I have one capital N that works for all x at the same time, and that concludes the proof. Just one last comment. It's the appearance of the less than or equal to sign in the limit that led me to choose epsilon over 2 to begin with, so I would end up with a strict less than epsilon to fit the definition. In some versions of this proof, you won't see that step. They'll just make a note that if it's less than or equal to epsilon, then that's good enough, but we haven't really talked about that, so I chose the epsilon over 2. All right.